class. Second thing is what you really should care about in the advanced class, right? Is a project should be something. For creativity's sake, that's not okay. So it has to be something that is being produced during the time frame of the class. Yes.
Okay.
I guess the Suvrit will also be throwing out some project ideas occasionally. I'll mention one or two things next week on Monday.
Yeah.
The other thing is office hours. We probably need to have some.
Well, I'm doing by email appointment only because I don't want to block a fixed amount of time. But we can see depending on how much interest there is in office hours.
So what I will be doing is I'll be available after the class for maybe about half an hour or so. If you, and this is the opportunity then to grab me and ask for some more time if you want to discuss something specific. Right? So, because otherwise sometimes you get office hours and nobody shows up and it doesn't cross everybody's schedule. So I'll be around after class for about half an hour, and this should also help, asking things, resolving them. Okay.
Okay.
Last but not least, this class is for you guys. So the more feedback that we get, the better. And the feedback can very well also be something like, hey Alex, your class was completely ununderstandable. Please explain better. Or, hey Suvrit, you don't have to go into that much detail, right? So, or maybe the other way around. Or, by the way, I find this really boring. Can we do something? Can we cover some other specific topics? This is a new class. It's never been in a syllabus before anywhere that we know of. It's basically so we have a bit of flexibility.
Okay.
So feedback will get you the result that you want, and it'll help us also make the class better.
Okay, I guess the last admin announcement that I have for you today is, by the end of this class, your homework 1, which covers really rudimentary convex functions and convex sets, we decided not to include any of the metric space convexity questions in there. I don't know how it got decided, but they are not in there. But we'll revisit those when I teach you about geometric optimization. But homework 1 will be uploaded to the class website, and the speed at which the homeworks are not very long. Some of the questions might be non-trivial. The speed at which we'll run these homeworks is like you get about 1.5 weeks. So the homework that gets released today will be due in class the next Monday. That means the 3rd of Feb, I think. And this will be the frequency. So today's Wednesday, next Wednesday plus the next lecture. And the homework, very importantly, remember the guidelines for doing the homework, whatever academic honesty standards, etc., all these important things, they are all written on the class webpage. But most importantly, the homeworks will be uploaded to EasyChair. There's a link to that on the class webpage. And I recommend to you, sign up for EasyChair before the deadline, okay? Because if you try to sign up on the day of the deadline and there is some problem, you might not be able to make the deadline, and then that leads to unnecessary email and admin hassles for us. So sign up for that website, and each homework is like a mini workshop paper. It's not like a paper, but I'm saying the way it's being handled. So, and we, as I announced in the beginning, we'll be doing peer grading for homeworks. You'll grade your peers, we'll provide an answer key. And this grading part also carries some credit so that you do a good job. So we'll come to that. So I guess if you have any other questions really related to the class, rather than bombard me or Alex with emails about the class, because the question you have, others might also have, just post it to the Google group so that one question gets answered for once and it's in a searchable repository, etc. Unless you're extremely uncomfortable asking that question, but the goal is at no stage to be uncomfortable asking anything, okay? Because those who stay quiet and not ask, sometimes they don't really learn what's going on. So far I've been covering some basics and I've been telling you some less basic material, and today is in some sense you can say the last basic class, and we are now going to enter doing optimization. But let me just quickly recap from last time a couple of important things just to remember what all we should remember take from last class. So one was this most important theorem, right? Which I think I made a typo while writing, is convex in X for each y taking a value in some arbitrary index set. Then the function obtained by marginalizing out by taking suprema is also convex. That's easy to verify because of sup being subadditive. And from this we obtained, you can say, by far one of the most important special cases, which is the so-called Legendre-Fenchel conjugate. Notice h of x comma y has to be convex only in x. It can be God knows whatever in y, okay? So special case was, this is just to remind you, you're supposed to kind of already know these concepts from convex optimization, but some of those are so important that you cannot repeat them often enough. Okay, I made, just to make it consistent with the line above, I changed my notation a little bit. So now there's a very interesting fact about Fenchel conjugates, okay? And so one of the things is, these are also, so some of the things that I'm recalling here, because these are standard theorems. Of course, in the book on convex analysis optimization, there are hundreds of theorems. These are like selected theorems. So if you look back at the book, you can maybe with a focused eye see, okay, these are some theorems that I should really know. Because they are basic material, I'm not going to have the luxury of time to prove all of them, but out of the hundreds of possible theorems, some of the important ones I'm pointing out to you. Later on, as we look at maybe newer material, then I will enter into more proofs. Though, of course, the burden of the proofs will be ultimately relegated to class notes so that we can cover more ground in class. Okay, so if I told you this very nice class of closed convex functions, which means whose epigraph is closed, and we are usually interested in closed convex functions so that, because these are easier to minimize. So for these, so if f is a closed convex function, then the conjugate of the conjugate is f. Okay, so these Fenchel conjugates is in some sense one of the ways, maybe the most important way, by which the idea of duality enters convex analysis. And this idea of duality actually enters maybe after somebody looked at a picture long enough. It's like, suppose f, this is a convex function f, I just made it smooth. The part above it is called its epigraph, right? and the epigraph being a convex set is same as F being convex. They are equivalent, whichever definition you like. Now, this set, the epigraph, can either be defined using the way we did, right? Epi of F is just where all those x where f of x is less than t. Now, there's another way to define this set, and that is by looking at, like we saw in the first class, if you have a convex set, there are two ways to look at it. One is, this direct characterization. The other is by characterizing it by the lines which support it, as in which bound it at its outermost periphery. And so that's another way. And what does that really mean? Well, maybe pictorially or analytically looking at it, if you have a convex function, right? At each point, there's a bunch of lines which underestimate it globally. So there's several, you can say, linear underestimators to a convex function at each point. And if you have a bunch of, gazillions of these linear underestimators, you might say, give me the best one. So let's say we define L of x as the tightest, smallest gap, like that. So this gives the tightest linear underestimator, and this is really nothing but, this is where the idea of the Fenchel conjugate comes from, because if you just take the minus of that inf, you get that guy. So that's how people, when trying to think maybe geometrically, they came up with this idea of Fenchel conjugate. I'm going to tell it in a non-geometric way now, something very recent but very interesting that I learned about Fenchel conjugates. So this is quite a recent theorem from, I think, 2007. So it's not yet in any textbook, but it makes us think. So let's see. So one definition, I'll use this notation, gamma 0, that's industry standard notation, is the class of closed, also known as, I'll come back to this later, lower semi-continuous or LSC convex functions. And the Fenchel conjugate up there, F star, we can say the way it is created is we consider something which we'll call a transform. Let's say L. L transforms members of the class of closed convex functions. Means it applies to any function, but let's restrict our attention to these closed convex functions. So L is some operation which takes members of this class into other members of that class. So that F star may be just written as that L of F at x is defined by that standard notation that we have up there. So far nothing has happened. I've just rewritten it to highlight that operation is done so frequently that just put a star for it, right? Just like when you take transpose of a matrix, we no longer really write a linear operation on a matrix. And the transpose is a linear operation, but we don't really write it, we always write AT or A star. We don't spend so much time writing whatever linear operation on A. But now we want to highlight that this Legendre-Fenchel transform is a transform on this set. And there's a very interesting theorem related to that, which I think I'll write on this side, is the following theorem. And after this, I'll pose a research question for you. So let T be any transform on this entire class gamma 0 to gamma 0, such that it satisfies the following two axiomatic properties. T applied to F is F itself. So I already wrote that up there as third theorem, F star star is F. And here is the duality part of it. Again, this is purely algebraic right now. There is no geometry. The proof requires some of that. So this is for every F. And for any two F comma G belonging to that class gamma naught, such that F is less than equal to G globally, implies transform of F is bigger than equal to transform of G. So if T is any transform which has this property that it's sort of involutory, which means T applied twice kills itself, and it has this order reversing property, then something really nice happens. This is then there exists a constant C, a vector. So this there's an Rn in there, finite dimensional Rn in there, and a matrix, invertible matrix in GLN, right? Such that T is essentially the Legendre-Fenchel transform. So if on that class, if you were to think what is so magical about this Fenchel conjugate, it is essentially the only transform which satisfies those axiomatic properties, which means that what that essentially means is the following, that Tf of x is nothing but Lf up to essentially a linear transformation. So that's a remarkable theorem by Artstein, Avidan and Millman. I'm not going to prove it here because the proof is an entire paper in the this journal, Annals of Mathematics, which is the leading journal for math. But it's a really nice result which shows that the reason I like such results is because, you know, like you, I like to say maybe play with these objects, and once you're playing with these objects, you might think, okay, Fenchel came up with his conjugate, I'll come up with mine, right? So you might investigate what other fancy transformations could you do on this class which have nice analytic and geometric properties. Maybe that's how you discover new properties. This theorem says that forget it on the class of closed convex functions, because Fenchel transform is essentially the only transform that has those nice properties. The way these things are proved, this is proving things for an entire class of functions. So it uses some ideas which I won't be able to describe fully, but maybe I can give you some insight. So the class of convex functions is also a convex cone, right? Non-negative combinations of convex functions, non-negative linear combinations of convex functions are again convex functions. And once you have the entire class is nothing but a convex cone, you can try to now bring some ideas from convex geometry to see how this cone might be represented. And once you have some kind of basis to represent this cone and you prove a theorem for the basis, it will carry through to the entire cone. But this is a very high level idea where people basically are generalizing their intuition from the world of linear algebra to the world of convex algebra. Anyhow, so the interesting thing I wanted to mention to you here is, suppose instead of the class of closed convex functions, you pick class S of your favorite functions. So S might be whatever, you know, log convex functions, or S might be these geodesically convex functions that we looked at, or some other distinguished class of functions. So one way, if duality theory does not yet exist for this class of functions, one way of discovering what might be a duality theory for this class is to now replace that gamma 0 by S and try to see, can you construct transforms on this class which satisfy just these two axiomatic properties. It's easier said than done, because if you look at the so if S is the class of, say, these geodesically convex functions, that means we have some mega convex geodesic space, etc. I don't know what should be the correct Fenchel transform on that set. Maybe it's easy to define, but it means I haven't given too much thought to it. But discovering a good conjugacy transform for that set will allow us to translate a lot of the convex analysis duality power to that other lesser explored class. So you can play, when you have free time, you can play with other favorite classes of yours. But this is a really nice theorem. Okay, now probably I don't know how many of you went to the recitation, but kind of I am assuming that you're familiar with the idea of subgradients and subdifferentials. I'll just mention a few interesting and important results in that regime here. For those of you who have not taken convex optimization, means I suggest that, so for those of you who have not taken convex optimization, or even for those you have, if you go to the class web page, there's a list of lectures and related material. In that list, there are a couple of links to my slides which summarize or present in much greater detail what I'm talking about from now onwards. So there is material linked to from the class web page in case you want to have a more leisurely look at or catch up with some of the concepts which you don't already know. Just go through those slides. So very closely related to the idea of that Fenchel conjugate is this idea, right, of subdifferentials. And as I warned in the beginning, unless I explicitly mention it, whenever I write f, I essentially mean f is a convex function in this class of closed convex functions. If f is at certain times allowed to be non-convex or geodesically convex, etc., I will point that out. But otherwise, if I forget to explicitly say that let f be convex, just assume it's convex. So, which means suppose f is right now arbitrary. To an arbitrary function, we can define, for an arbitrary function f, we define this set. There are several ways of coming up with this idea, but that belong to introductory chapters. So again, we are working in a vector space. That's why I'm writing all these linear operations here. Okay, for all. So just like I said, when we created that Fenchel conjugate, it was motivated by the idea of those global linear underestimators. The members of this set, which is called the subdifferential, give us global linear underestimators of f, which is why I said those two guys are really deeply connected. So here I did not require in this definition that f should be convex, because this property could maybe, if you're lucky, satisfied for non-convex functions also. However, it's maybe an exercise, but still a very important result actually, that if this set is non-empty for every x in the domain of f, then f must be convex. So there's a converse to that, which is an important result. So, which means that if we want to really generalize the notion of subdifferential to non-convex functions, which we'll visit at some point during the class, one has to do some other stuff. Okay, so if x does not belong to domain of f, that means f is infinity, then at that particular x, this is empty obviously, and okay, so a result now which formally what I just said right now, this gives global linear underestimator, and that's the Ferential conjugate, a result that formally connects the two. Let's write it on this side. Well, first notice from the definition f star of x is supremum of something, right? So from that definition you of course have that f star x plus f of y is bigger than equal to x transpose y for all x comma y. Again, this inequality requires that to actually be overcorrect while stating that inequality, we should enforce that f is not plus infinity everywhere. So functions which are not identical to plus infinity are called proper, because if f is plus infinity everywhere, by that definition f star will become minus infinity, and I think in lecture 1 or 2 I told you that we don't want to add or subtract minus infinity from stuff. So suppose f star is not plus infinity everywhere. So this is called the Fenchel-Young inequality. It's stated in other tricky forms, but it just falls out actually from the definition. But interestingly now, this theorem, I'm writing it as a theorem. So again, things that are written here as theorems are because they are important results. Not everything that is written as a theorem means it's difficult to prove, okay? Something that is given the status of a theorem is more to indicate its importance, not difficulty. We shouldn't mix those two. So, a vector g belongs to a subdifferential at x if and only if the above inequality actually holds with equality. Okay, I should stop abusing the alphabets here, so I'll already maybe write it in the way I'm using it. And you can verify that fairly easily by really just using the definition. Okay, there is nothing really to show there, but it's important because the reason it's important is sometimes it is, or very frequently it is difficult to deal with the set partial of f, this subdifferential, and instead of dealing with that set directly, we might try to attack it through the conjugate of f. So that's why where these simple equations can come in handy. Okay, the final important theorem that I want to semi-final penultimate important theorem that I want to tell you, I'll prove only one direction of this is, again, just like for differentiable functions, we have very well developed calculus regardless of convexity, right? For differentiable functions, you have the chain rule of calculus, which is by far the most important rule, product rule, chain rule, of course, and linear and whatnot. Really important calculus rules for dealing with derivatives of functions and combining derivatives. when it comes to non-differentiable functions, but functions that are subdifferentiable, we'll call a function is subdifferentiable at a point if its subdifferential set is non-empty. So for functions that are subdifferentiable, there is a corresponding calculus, but that calculus requires, at least the full power of it, requires that f be a closed convex function. Means if you want to have a nice chain rule of calculus and linear rule, etc., you need those. If f is non-convex, we don't have a very good working calculus available. And you can, just to see what even happens, just to get an idea why things could go wrong, just consider this simple function. Absolute value of x is non-differentiable, right? Absolute value of x minus absolute value of x. So this is a sum of two non-differentiable functions, which is differentiable everywhere because it is identical to 0. Each of those guys is not differentiable. So you can see that as soon as you leave the world of differentiability, things become a little difficult. But so let me tell you one of the most important theorems, and this theorem is important because we often implicitly use it while doing optimization when we appeal to something called constraint qualification. But this theorem is stated fairly simply. So let f1 up till fm be, let's call them proper, that is not identical to plus infinity convex functions on Rn, and suppose you add a bunch of convex functions. Is this true that what you would expect in the nice differentiable world we would love for such a linear rule to apply, because often when we are working with convex functions we might add them, right? At least under non-negative combination. Well, this rule is not always true, unfortunately. So, but under hypothesis, which when it really comes to checking that hypothesis, it's not so easy to maybe check that hypothesis. So if, I'll give you an explicit example of when this breaks down, but let me write the theorem for you first. Then, I shouldn't have erased that. This f of x includes and the theorem goes further, and let's push this to the this is kind of tricky, so let's complete it here. I have a nice blank board back there. So this theorem statement continues on the right hand side. Very nice thing happens here. So if in addition the intersection, if in addition the interiors of the domains of these functions, they have a non-empty intersection, and actually not interiors, the relative interiors. So if in addition this happens, the relative interior, so domain is just the set of points in Rn where the function is not infinite. So if this constraint qualification condition is satisfied, then actually that then you actually have this equality. And this will now look a little familiar. If some of these convex functions are actually polyhedral, then in fact the intersection, so suppose f1 through fk are polyhedral, then you don't need to look at the relative interiors, you just look at the domains that intersected with that intersection of relative interiors of the remaining. If that is not empty, then it's equality. So this looks fancifully stated, but it tells you that you have to be slightly careful that when you add two convex functions, that they should at least share some point, essentially, where the overall added function is not plus infinity. And why this is important is, remember last time I told you about an indicator function. So an indicator function is 0 when you're sitting inside the set and plus infinity otherwise, right? So if you had a convex set C1 and a convex set C2, you can have these such that their intersection is empty, then the indicator function of C1 plus indicator function of C2 will be equal to plus infinity everywhere. And this function, this is a valid convex function, but this function will not be subdifferentiable. So it is in some sense, this fanciful looking condition, all it is saying is that there is some kind of feasible point. And we'll come to that when I mention something called, you might have heard of Slater's constraint qualification, etc. It's related to that. Yeah.
So this notion of addition means set addition.
Set addition, yeah.
So if any of the sets is phi, the addition, the sum is phi, right?
Yeah. Oh no. A plus phi is A.
Okay.
Right? Because phi is like the 0 element of the set addition of sets.
Okay.
Set multiplication would kill, but not. So let's verify the easy part. The easy part actually, again, you know, these theorems are written in this way so that you can rely on them and use them. The proofs are actually not so difficult, which is the best part, right? So of course I'll prove only the inclusion part, which is, so say G is some vector written as G1 plus Gm, right? What happens then? Where Gi belongs to the ith subdifferential. What happens then? Well, so f of z is f1 plus fm of z, which by definition is bigger than equal to f1 of x plus g1, because g1 is a subdifferential for f1. This inequality is satisfied for f1. Similarly, inequalities are then satisfied up till fm, right? Now comes the nice thing that this inner product is linear. So this, you just rearrange this into f1 plus fm plus g1 up till gm of z minus x, which is nothing but, f of x plus g of z minus x, which proves that this g is subdifferential, that arbitrary g lies in the subdifferential of f of z, which proves the inclusion. The other direction requires some work, which is why I'm going to skip it. I'll write a short example here to make this thing maybe slightly less abstract. Again, this is a contrived example, but just like I wrote the summation of those two indicator sets, it's important to keep in mind that there is this constraint qualification that one has to worry about. So there is this example, f1 of x is, I had it down here, so square root of x is a concave function, minus square root of that will be a convex function on the positive reals. So, and we make it a function over the entire real set reals by making it plus infinity outside the correct domain, and f2 of x is evilly chosen to essentially of course this is created as a pathology to give you, yeah?
Why is it a superset and not
No, because we only proved one direction. We showed that anything that lies in that sum has to lie here. We have to also show the other direction, right?
Can you give an example there?
So this is the example where you'll see the example, wherein that's exactly what I'm trying to show you here. So now if you add these two functions, if you look at them, they're very close to my indicator function example. If you add these two functions, what happens? Well, f is equal to f1 plus f2 seems to me to be equal to 0 if x is equal to 0, infinity otherwise, right? That's what f1 plus f2 is. Now, if so, this is the indicator function for just 0. So, at 0, this subdifferential will be entire R, whereas you can verify this is specially chosen, square root of x, you know, is not differentiable at 0. The derivative becomes infinity. So you can see that actually is an empty set, So the right hand side is an empty set, but the left hand side is the entire real line. And this essentially what happened is that this set has empty relative interior.
Were you saying earlier that the sum of the subdifferentials isn't empty if one of them is? Was that the question earlier?
Yeah. What are you saying? You're saying that should be empty?
I was just checking.
There's a set addition. Okay, comes to the convention. Let me think about it. But so what I want to tell you right now is to see this material developed in much greater detail. This is in some sense reading assignment for you. Please go to the class webpage. Under the lectures, there's a link to slides where I describe these things in greater detail. And means you should have a look at that. And the whole point of bringing this up is most of the time we'll actually just say that the subdifferential of f is the sum of the subdifferentials. We'll most of the time work with nice functions, but it's good to keep at the back of your mind that sometimes this condition may fail. And in a very recent paper that I wrote, for us this very condition failed. So it's good to know that you know, sometimes it can fail.
One more question about the example, or about the sum of subdifferentials. Does that only hold if the functions are complex?
Yeah. So that's why when I wrote the theorem, it's gone at the back. I said let f1 f through fm all be convex functions. So unless I explicitly shout out and say this also works for non-convex, like I said, everything should be for safety assumed to be convex. Now, for the field of convex analysis, developing a nice calculus of subdifferential functions is one of the major achievements. So this is done during late 60s and early 70s, and this culminates and is described in a famous book called Convex Analysis by Rockefeller, written in 1970. To this day, it is the standard reference book for convex analysis. I think many of the basic results of calculus of convex functions and so on were developed by Rockefeller during his PhD. And now, of course, all those things are used, on a daily basis. So I think I'm not going to talk about the various calculus rules that we have for subdifferential functions. I just talked about one. There's a bunch of others which you might have already seen in convex optimization, like how to get the subdifferential. So we constructed a convex function by taking a soup of infinite family of functions, or whatever finite family of functions. How do we get a subgradient, or how do we define the subdifferential of that type of function? So again, interestingly, if the functions are everywhere finite, that set is fairly easy to describe. But I think only 1 or 2 years ago, somebody finally wrote a paper which says completely characterizing the subdifferential of soup. So you might think that many things are classical, like I said, subdifferential calculus is well developed, but getting the dirty corner cases, people have only very recently managed to settle. But for us, like I said, throughout the rest of the class, we are looking at ultimately, we care a lot about real world engineering applications. And for us, we'd better start off with good functions. Otherwise, maybe our model is not so nice. So those technical details optimizing over, it can get confusing. So from day one, make the convention that whenever you write down an optimization problem, explicitly tell the reader what the variable is. So we know that if f, from maybe high school calculus, we know that if f, at least in one-dimensional case, if f is differentiable, then if f is once differentiable, say, we know that gradient of f of x star equal to 0 is a necessary condition for x star to be local optimum. So if f is any differentiable nonlinear function, not necessarily convex, this is called the first order necessary condition of optimality. The luxury of convex functions is that this local condition also is not only necessary, it's sufficient, which makes the class of convex functions distinguished. A brief exercise for you actually, the class of convex functions is not the only class that enjoys this luxury, right? Let's write a huge generalization but a useless one to show you that sometimes generalizations are useless. So for convex functions, what did we have? We had something like f of x. This is the first order definition of convexity, right? And hence, if f of x is 0, this holds for all y and x, this proves by definition sufficiency of that condition. So more generally, you can say, I'm in the mood to generalize, so I make the following generalization. I consider f belonging to some fancy class of functions, let's call it C, which satisfies a similar property. Fy is bigger than f of x plus some function of the gradient and x and y, where this function satisfies the property that C of 0, this is 0. So if you have a class, fancy class C of functions for which you can show this representation, for that class also gradient disappearing is a sufficient condition for global optimality. Some people took this really far. They created a class of functions that is called invex functions, where they wrote this as the definition. But what sucks about this definition? Well, what sucks about this definition is really testing it in the first place. It's for convex functions we have now, I didn't tell all of them, but we have tens of methods of testing membership in the class of convex functions. If I give you this funky class C, you might not be able to even test membership in that, so you might not be able to use that. So you will find a short Wikipedia page article on something that is called INVEX, INVEX functions. People have even written a book about that, but it's also been heavily criticized by people in convex analysis because really ultimately of this problem, you don't know how to test membership in that class. However, a brief exercise for you. Suppose you have a differentiable but that Menger convex metric, that geodesically convex function. For that, a similar inequality does hold and we can test it. So just to tell you that the class of ordinary convex functions in Euclidean space is not the only one with the luxury of sufficiency, but it is by far the most well-known one. Okay? So some other stuff happens. Yeah, it's worth actually mentioning at this point. So checking the gradient is close to 0 is in some sense an easy condition. Means numerically you can test if the norm of the gradient has become small, right? That might be a typical thing to check on a computer. But honestly, beyond that, it's not so easy to reliably check because the norm of your gradient could have become quite small on your computer, even for quite a non-convex function. So the problem with this world of non-convex functions is that suppose we could do this in exact arithmetic, whatever, we do not have an easy to check necessary and sufficient condition on optimality. You have a necessary condition, but we don't have an easy condition on a sufficient condition on optimality. For non-convex functions, sometimes even testing local optimality can be NP hard. So most of the times there we just try to satisfy for non-convex differentiable functions condition of local this necessary condition. However, we do have, if the function is twice differentiable, then if the Hessian matrix at the point x star is strictly positive definite, then that x star is a local minimum. These are like standard results in nonlinear programming, but just I'm reminding you. And unfortunately, if you are faced with a difficult looking non-convex function, testing that itself might be quite hard because as you get into multivariable calculus, computing Hessians is rather burdensome. That is why I try to avoid it. Sometimes there's nothing to do, but so now let's leave the world of differentiable functions and see something for general convex functions now. I didn't search into why it is called the following, but this thing is called Fermas Law. So other than writing things in margins, he also made some other theorems. So this is a standard one. So let's say f is a convex function and we allow f to take on the value plus infinity, and then the set of minima of f. Okay, so this is the set, this is the collection of vectors in R to the n where f achieves its minimum value. This is, it coincides with the set of zeros of its subdifferential. So this is really generalizing that differentiable thing to the subdifferentiable world, which is defined as just what I said in words, R to the n, such that 0 belongs to, so this is a nice result. So this generalizes, so this is an if and only if, okay. So this generalizes the differentiable world to the non-differentiable world, which suggests that perhaps when we try to test optimality, it might be good to know how to compute subdifferentials. When writing an optimization algorithm, it's okay if you know how to compute a single subgradient. You don't need the entire subdifferential set, which is a very difficult set to describe. But maybe when doing theoretical analysis and optimality, sensitivity, stability of your solution, etc., then it's good to know this set. But anyhow, the proof is simple, right? So let's write it out. It's a short but nice proof. So if actually one direction and the other direction, they're essentially the same, you'll see. So if x belongs to, suppose x is an alleged minimum, right? Suppose, then what happens? Then fx is less than equal to fy for all y. Well, I just flip it around and write that fy is bigger than equal to f of x plus 0 times y minus x, right? So which shows that, which implies that y belongs, that for all y, 0 belongs to this minimum and vice versa. So easy to write, very nice condition, but we have very quickly, merely from the definition of subdifferential set, generalized the first order necessary and sufficient condition of optimality to non-smooth functions. So now let's put this into action and derive something that is usually derived in maybe rather complicated way, but we'll just get it as a consequence of this definition. Did I send it back there? Maybe I'll also first simultaneously draw this picture of mine, which you might keep in mind. So I'll make a picture kind of drawing the level sets of a function. So this is value of f at c1, f of c2 is smaller than f of c1. So these are the level sets of a function. And suppose we are trying to minimize it. Subject to some constraint. So we are trying to minimize f of x subject to x belonging to a compact convex set here, script x. This is script x. Well, this is so-called, this is minimum. This is the, suppose f is differentiable as shown here. So we will recover this condition that at an alleged minimum, the gradient, because it's a constraint problem, the gradient is not 0, it forms an acute angle with any feasible y. That's that picture for all y belonging to x. So this is derivable in several ways, but we'll derive it using that definition right now. It's a short little proof which illustrates one use of subdifferentials that I like. So first of all, notice that constrained optimization problem can be written as a problem over entire Rn by writing it as fx plus indicator function. So that is first time we are actually using that indicator function just for change of notation. And a lot of the time when doing convex optimization or optimization in general, the entire game is in transforming your problem to look nice so that it becomes solvable. So this is but purely for theoretical analysis right now. So now apply that rule. So, if we apply that rule, I'll actually use a couple of theorems that I presented to you already. So X star belongs to the set of minima. I assumed that set X to be right now closed and compact, so that by Weierstrass theorem we know that our continuous function will actually attain its minimum on that, but that's an aside. But suppose, so this set is non-empty. So suppose X star achieves that, then by Fermat's rule, 0 should belong to F plus at X star, right? So that's necessary and sufficient. And now you see where something which is called sometimes Slater constraint qualification, X is a convex set, where that so-called constraint qualification now comes in, is while trying to simplify this. So this is subdifferential of a sum of two convex functions. To simplify our analysis, we want to write this as a sum of subdifferentials. So for that, we assume the sufficiency part, which is just sufficient. Some people who like to do painful things, they still write papers about weaker and weaker sufficiency conditions, but it gets really hairy, so we are not going to entertain ourselves with that. But so we'll assume, for applying Rockefeller's theorem, we'll assume that the relative interior of domain of F intersected with the relative interior of the domain of the indicator, which is nothing but this. This is not empty. So this is, usually people don't explicitly write that out, they just say it satisfies a constraint qualification condition, but that is so that we can write 0 belongs to f of x star plus subdifferential of the indicator function at x star. So all that remains is just more notation. So this actually already gives you, so this characterization contains this particular characterization as a special case. Let's see quickly how. So, well, f is subdifferentiable for now. Let's try to just rewrite what the subdifferential of the indicator function is, right? How do we write that? Well, just by definition. Okay, let's just actually erase this. Is more. The other part I leave for you to see. Okay, so just to describe this the subdifferential set of that, you'll just have, just throw in, just crank the definition. G belongs to a subdifferential of that guy at a point x if it satisfies this for all y. So if we are particularly interested in the value of the subdifferential at x star, so x star is an alleged minimum, so it had better be feasible. That means delta x of x star will be 0. So you will just have this is for all y. For y that are not feasible, this holds trivially because this guy will be infinite. So the only time this thing is a non-triviality is essentially, and if y is feasible also, this becomes 0 is bigger than g of this inner product for all feasible y. So now this particular set, this should be an x star, sorry, because I got rid of delta x. So this particular set the subdifferential. This comes up notationally many times, so people create a separate notation for that. The subdifferential of the indicator function at a point x is called this particular set, the collection of all such G for which this inequality holds. That's a convex cone. It's called the so-called normal cone. So in fancier notation, the optimality condition has boiled down to saying that 0 belongs to subdifferential f of x star plus normal cone at x star. Now, again, remember, this is all just so far notation. Nothing deep happened at all. The depth happened when the definition of subdifferential was created. That was the deep part. After that, it's just manipulations. And with this manipulation, suppose f is differentiable. F is convex and differentiable. Then its subdifferential set is a singleton. And what is that singleton? Nothing but the gradient. So suppose f is differentiable. Plug in this definition and do a little bit of algebra, which I don't want to spend time doing. You will end up getting this as a special case. So you got a necessary and sufficient condition for convex optimization as a special case of mere notation manipulation. We are not so happy yet with that, because in practice, testing this sufficiency condition is really hard. We are never really going to test this condition. But it's there just to show you that standard sufficiency condition, maybe there's a rare problem that you have in your work where you actually can test this condition. But to show you that some standard results on optimality could be just recovered as after some notational manipulation. Okay, so the research oriented question here would be to look at similar optimality conditions, but in this geodesically convex metric spaces that we talked about, because there it's not even clear in general who plays the role of a gradient. So people who create the subject of differential geometry, they create that subject by creating the notion of essentially derivatives in these curved spaces. But we are looking at even more general metric spaces, so it's not always so clear what the corresponding notion. So extending these classical results, they are worthwhile things to think about, but it's not so clear. Anyhow, but the first order condition, if you somehow are given a local somebody tells you this is a local optimum, for that geodesically convex space also that will be global. So that part we can prove. But otherwise, coming up with nice necessary and sufficient conditions, if those functions are differentiable and somehow embedded into Rn, then you can just apply the differentiable condition, but otherwise not. So before I now spend too much more time on this, now let me just mention to you a few standard classes of optimization problems that we will meet now and then, again and again in this class. So the very first one, I think this guy can come down now. So in general, we might just write minimize f of x plus g of x, and this is over entire Rn, where f and g are convex functions. But more specialized, probably everybody has seen maybe the simpler case where actually the story started, like everybody has seen linear programming, right? So in the world of linear programming, it has a distinguished place. So I'll write what is called a standard form linear programming problem. Linear objective function. A linear function has the special property that it is both convex and concave, which kind of makes linear programming nicer. Linear equality constraints and a non-negativity constraint. So that's a standard form linear program. And around World War II time, when Danzig thought about that, means playfully, actually, you know, one might think, how did, say, somebody come up with the idea of linear programming? So, and the name linear, etc., right? So one way maybe they might have come up with that is, you had been solving linear systems of equations for a long time, ax equal to b. Somebody wanted to play with stuff and said, but wait a minute, what if I replace that equality with an inequality? I have ax less than equal to b. I don't want an exact x, can I find some x which satisfies these inequalities? And just this mere playing with things creates an entire field, right? Once you start trying to answer this feasibility problem, the next step, which was, again, in hindsight, everything looks simple, but this was one of the, you can say, remarkable insights of Georg Danzig that time. He said, okay, we have these linear inequalities, they represent some constraints, and we are trying to find some feasible solution. There are gazillions of these. What should we do? You know, so what was the insight? He added a cost function. Out of all the, and the cost function was linear. Out of all the possible solutions, let's somehow assign a cost to each. That's why historically this is often written as C to indicate cost. Out of all possible solutions, let's somehow measure their cost, and thus was born, you can say, linear programming. And then, of course, it had huge success. Then people thought, what could be potential ways to generalize linear programming? And hence was, of course, born nonlinear programming. But if you look at that, again, as I've already shown you, some generalizations are useful. Some are just generalizations for the sake of generalization. So there, this standard linear program, which is used, was used so much, there are three places in which we could generalize it, right? You could replace the cost function by a nonlinear cost function. An arbitrary nonlinear cost function, of course, turns it into a difficult non-convex problem. But if you replace that by a convex cost function, then you have convex optimization. Just that simple change. The ax equal to b, those are affine linear constraints. You might think, let's replace the map A by a nonlinear map. But very quickly, things become tricky. So for example, suppose I replace just this linear constraints by something very simple like this. Xi square is equal to 1 and some other simple constraints. This constraint is just nothing but xi is equal to plus 1 or minus 1. That's not a linear constraint, is maybe one of the simplest nonlinear constraints you could think of, and you've already left the world of what is tractable and entered the world of non-tractable NP-hard problems. Because with that you reach integer programming. So ordinary, just playing around, so it somehow tells that this problem is little delicate. Well, but people still didn't give up. They said, let's keep the objective linear, because we had already thought about convex. The third thing that remains is the last constraint. So the last constraint may be looked at as a constraint, or it might be looked at as what is called a structural constraint. So x is required to live in the non-negative orthent. What is the non-negative orthent, as we saw in lecture 1? Non-negative orthent is a certain cone. So this was a deep idea during the 80s. A lot of it was developed by Yuri Nesterov and Arkady Nemirovsky in fundamental theory of conic optimization, where essentially the insight is this part gets replaced by a generalized inequality that x should live in some cone. And which kinds of cones work? So, and that generalization, and that is really very beautiful theory in the theory of interior point methods and conic programming that they developed that shows that almost, not everything, almost everything that you could do in this linear programming world could be extended to the conic programming world. And of course, not every cone works. We are trying to look for meaningful generalizations. So the kinds of generalizations you search for are which kinds of cones give rise to useful inequalities. And I'm out of time, but you will see soon when Alex starts talking that the cone of n by n symmetric positive definite matrices gives a really nice generalization to this, which is called semi-definite programming. Again, that K need not be the cone of semi-definite matrices. It could be some other convex cone. Not every convex cone will lead to tractable problems. Remember I mentioned the cone of co-positive matrices? That cone is a generalization, leads to co-positive programming, but not so useful because, again, testing membership in that cone is co-NP complete. So with this cone, if K is this cone, then this problem is what is known as semi-definite programming. And I'm out of time, but I think Alex will show you now later in the next lecture some of the cool things you can start doing now with once you have gone from the linear world to the conic world. And later on in the course, I'll give you maybe a richer set of examples of many other difficult looking optimization problems which can be transformed into ordinary conic programs. Okay, see you later.